In this project, we integrate restaurant-level data from the Yelp Open dataset with county-level economic indicators from the Bureau of Labor Statistics, BLS, and the Bureau of Economic Analysis, BEA, to construct a unified analytical dataset. The primary goal is to understand how local economic conditions interact with small business operations, focusing on U.S. restaurants. Yelp provides detailed business-level information, including star ratings, review counts, operational hours, categories, and attributes. On its own, Yelp data is insightful, but it lacks context on the local labor market and broader economic environment. By combining Yelp data with BLS and BEA datasets, which include county-level labor force size, employment and unemployment statistics, and GDP, we can place each business in its socioeconomic context. This enables the exploration of questions such as, are restaurants more likely to close in counties with high unemployment? How does local GDP relate to small business density or longevity? And can shifts in economic indicators predict regions primed for new openings? The integrated dataset thus provides a unique opportunity to study the intersection of micro-level business characteristics with macro-level economic conditions. This analysis examines a dataset of 439,596 small businesses with the objective of predicting whether a business is open or closed. The dataset combines business-level attributes from Yelp, such as star ratings, review counts, categories, and operational hours, with regional economic indicators, such as labor force, employment, unemployment rate, and GDP, enabling a holistic assessment of factors influencing business longevity. As for the dataset overview, the size and structure includes 439,596 rows and 21 columns. The business features include business ID, name, address, city, state, postal code, latitude, longitude, categories, attributes, and hours. The economic indicators include labor force, employed, unemployed, unemployment rate, and GDP. And finally, the Yelp-specific metrics include star ratings, review count, aggregated review features. Our key observations included that numeric variables such as star ratings and GDP are suitable for direct modeling, while categorical variables such as city and attributes require encoding. Missing data was present in some columns as well, such as hours missing for 67,500 rows and attributes missing around 40,000 rows. Critical numeric features have minimal gaps. Summary statistics highlight wide variation in economic and review-based metrics, indicating a need for normalization or transformation.
From our initial exploratory data analysis, we examined the distribution of key covariates. Histograms and kernel density estimates were used to visualize numeric covariates. We found that the labor force, employed population, unemployed population, and GDP are right skewed, with some outliers present. We found that star ratings cluster around common values, such as 3, 4, and 5, and review counts are heavily skewed, with few businesses accumulating large numbers of reviews. The implications of this are that skewed features may require log transformations for effective data modeling. Categorical features with rarer levels could be grouped for dimensionality reduction. For our target variable analysis, the distribution of business openings shows class imbalance, with about 80% of businesses open and about 20% closed. The review-based metrics differ by business status. Open businesses generally tend to have higher review counts and slightly higher average ratings than closed businesses, while the closed businesses concentrate around those lower values. This imbalance suggests a potential need for stratified sampling or class weighting in predictive modeling.
So here are a few of the key insights that we got from our visualizations and statistical summaries that informed our pre-processing, feature engineering, and model selection choices. First off, we see that the economic indicators do contribute to predictive modeling, but they require careful scaling because of the way that they're distributed. Another insight is that we see that the aggregated review features are informative, but they're not sufficient to distinguish the business status. Another important key insight is that the distribution of different features by class is pretty similar, so we can be relatively confident that there's no bias and no error there. We also see that the data is class imbalanced, which can impact our minority class prediction. In the future, we'll want to handle this imbalance when we refine our model. To conclude, we can say that this EDA establishes a comprehensive understanding of business level and regional level features and how they relate to the business status. The combination of distribution analysis, target stratification, and review level aggregation provides a strong foundation for predicting whether a business will be closed or open. Our future work will focus on addressing the class imbalance, exploring additional features, and refining the model performance for closed businesses.
County shapefiles and coordinates in the Yelp dataset to assign businesses to counties with the GeoPandas spatial join feature. Then, we use county FIPS code to join them with our economic dataset. We engineered multiple variables to convert unstructured text and operational data into interpretable, model-ready features. We quantified the number of categories from comma-separate category lists and attributes from dictionary-style fields for each business. These variables capture the breadth of a business's identity and complexity. We also derive total weekly hours, number of days open per week, and average daily hours from the business hours field. These features provide insight into operational intensity and potential market reach. Millions of reviews were then condensed at the business level. For each business, we computed the weighted average number of stars by the usefulness rating that the reviews got, the total number of reviews, and the weighted average review length. For tips, we calculated the total number of tips given, the weighted average tip length by the tips complement count, the complement count, total complement count, and average complement count for that business. Then, using Vader sentiment and applying it on all the tips a business was given, we generated a tips sentiment score ranging from -1, very negative, to +1, very positive. This captures the overall tone of customer feedback and enriches our predictive features. Note a limitation of our analysis was that we could not apply sentiment analysis on review text because they were too long and we were limited by our computing capacity. We then concatenated all reviews and tips text for our textual features. To implement these features into predictive models, we applied TF-IDF vectorization to reviews and tips. This approach captures the relative importance of words and word pairs while limiting dimensionality to the top 5,000 features. We filter out terms with fewer than 5 occurrences or appeared in more than 80% of documents to capture as much meaningful context as possible. The resulting TF-IDF features were combined with our numeric attributes to create a high-dimensional feature set of over 5,000 columns. We then applied z-score normalization to all features to normalize their ranges. This ensures that numeric and text-derived features contribute comparably to models, preventing features with large magnitudes from dominating our learning algorithm. We trained 2 classifiers to predict business status. The first one is a bagging classifier using a logistic regression model as the base estimator, and the second one is an XGBoost classifier. And our results was that the logistic regression bagging classifier achieved an accuracy of 76% and an F1 score of 0.76. This ensemble approach mitigates overfitting and leverages the stability of logistic regression in high-dimensional settings. Our XGBoost classifier did a little bit better at 78.5% accuracy and an F1 score of 0.79. This outperformance demonstrated the robustness in handling mixed numeric and sparse textual features. We also plotted an ROC curve with the area under the curve at 0.87, which confirms a strong balance between true positive and false positive rates, and that our models were successful at predicting business closures. These results indicate that combining numeric attributes with text-derived features improves our ability to predict business status, highlighting the value of both operational and customer feedback data. To understand what drives the XGBoost model's predictions, we visualized the top 20 most important features. Key contributors included textual features derived from reviews and tips, reflecting customer sentiment and behavior and the quality of the business. There were mentions of COVID, which was a major predictor in identifying business closure probability. The numeric business characteristics, such as the number of attributes for that business, was also a major predictor. But a limitation was the inclusion of the word closed, which signals to our models that the business was closed. This analysis enhanced our model interpretability and provides guidance for feature selection, data collection, and further analysis. So to conclude, through careful integration of business level and county level data, systematic feature engineering, and predictive modeling, we constructed a robust analytical pipeline capable of examining small business dynamics. The combination of structured numeric data and unstructured textual data enables both accurate predictions and actionable insights. Our approach demonstrates that local economic conditions, operational characteristics, and customer sentiment collectively influence business outcomes, providing a foundation for future analyses of small business resilience and growth.